There you go.
Nice, thank you. Yeah, so I'm talking about SPT phases, SPTs, and so in case it's not completely obvious already by the title slide, this presentation was made last night at like 12:30. So uh, it's going to be incredibly casual, and I haven't practiced or anything, so hopefully it'll just be fun. We can talk about things, have discussions. Yeah. So okay, so SPT, what does the acronym stand for? The acronym stands for Symmetry Protected Topological, and then SPT phase is the phase part. And I don't know how widely known this anecdote is, but when when we were taking Xiaogang's class on quantum matter stuff a few years ago, I think he likes to say this anecdote where so Xiaogang and his collaborators were the people who kind of came up with this idea of a SPT, and when they were writing up this work, they had initially called them symmetry protected trivial phases, which is sort of in some sense a better moniker, but they wanted Zheng Chenghu, who was on the paper, to get a job, and they didn't want to call it symmetry protected trivial phase because that sounded kind of lame. So hence we were left with the name symmetry protected topological phase, which makes a non-zero amount of sense, as we'll see, but maybe trivial phase is the better thing to work with. Anyway, so okay, what is an SPT? So there are many different ways of kind of saying what a SPT is. Some of them are just semantically different from each other, but some of them kind of like actually define different things. So for the purposes of this talk, an SPT is going to be this definition here. So an SPT is going to be a system that has a gap, has some symmetry group, G, and which is furthermore such that if you consider this system on any manifold, the ground state is unique. And so this is what this means essentially is that the partition function, if I look at the partition function of the system on any manifold, it's just the number 1, right? Because there are no gapless degrees of freedom. So and also there is a unique ground state on every manifold, right? So people are familiar with topological order and gauge theories and stuff like this. These are also systems where you have a gap. You can think about them as having some symmetry, but if I put something with topological order or something on a manifold like this, it'll have some ground state degeneracy, and if I put it on a manifold like this, it'll have some different ground state degeneracy. And so we're not interested in cases like this. We're just interested in the case where there's just one ground state, a unique ground state for everything. Okay. And so then you may say, okay, what is the point in, well, yeah, can there possibly be anything non-trivial that fits this definition, right? In particular, why did you tell me about this symmetry group G if the partition function is just going to be 1, and if there's a gap and a unique ground state, right? Because normally, what do we do with symmetries in normal physics, right? Well, symmetries are useful because if you have a symmetry G, then you can write your Hamiltonian. Symmetry G means to have a bunch of operators which commute with the Hamiltonian, and you can write the Hamiltonian as a giant block diagonal matrix, where each of these blocks is indexed according to representations of the symmetry. And then this is useful because then we have a way of organizing the spectrum of the system, and we have things like conservation laws. So we have some particles carrying some charge under the symmetry, and we know there are some selection rules on the way in which they can fuse together, and selection rules on amplitudes and all this stuff. But okay, if the system is gapped with a unique ground state, then there's no real Hamiltonian, right? The Hamiltonian is essentially, well, if it's gapped in a unique ground state, then at low energies we don't have to worry about the Hamiltonian at all. So there's no spectrum really to organize according to representations of the group. There's no scattering or anything to put selection rules on. So what's the whole point of having a symmetry at all? And so the point is that if we have a symmetry, then we can look at then we can look at what happens when we couple the system to a background field for that symmetry. So what that means is, if I have some symmetry, then I can couple my system to some gauge field A for that symmetry, and I can look at the partition function in the presence of that gauge field. So if this is if my symmetry, for example, is U1, then what I would do is I would look at some term where I take the current for the symmetry and I would couple it to some field like this. And then I would study what happens to the system in the presence of this background field. In the case where the symmetry is some discrete symmetry, or maybe a space-time symmetry or something like this, where this current operator is a bit, let's just say where this current operator doesn't exist, then what I mean by coupling to a background field is I mean, taking a system like this and putting in some, this is essentially what coupling to a background field means. It means putting in some defects into the system where the defects are labeled by group elements, something like this, and where these defects are essentially charge operators. So as I pass from this region of the system to this region of the system, I get acted on by some representation of this group element here. So it's essentially like asserting domain walls. So what this means is that even though we might not have any low energy charge excitations, all the stuff charged under the symmetry is projected away, we can still examine consequences of having the symmetry group in the fact that we can add these operators into the system. We can add these like domain walls into the system. And then we can study the properties of these domain walls. Okay. Now, since I told you that we have a unique ground state and gap and everything, this partition function here, so in the present, and without any added domain wall stuff, any gauge field stuff, this was just 1, right? As I set up here. And now when I add in a gauge field, the partition function can't become anything with a magnitude that's different than 1, but it can become a phase. So it becomes some complex number. And so essentially what SPTs are is they are systems where when you add in domain walls, or you couple the system to some gauge field, the partition function becomes some non-trivial phase factor here. Okay, I think that's all I want to say about this. Okay, so we'll get to, so we're going to get to some examples in a sec to see how actually you can couple a gauge field to something that seems this trivial and still get something interesting out. But for now, I'm just going to talk about sort of general things. Okay.
Ethan, just one question. So what does it mean that the phase is non-trivial? So that you cannot gauge it away, or
oh, what? Like so yeah. So the what this means by being non-trivial is that, well, okay, if my partition function is some number, some number, any partition function that is not 1 is non-trivial in a sense. If this actually depends on A, in some sense it's non-trivial. But one stipulation here is that, which I'll get into later, is that if you allow yourself to break this symmetry G, then, as we'll see in a sec, then this Z of A can be turned into 1, sort of. So if you break this the G symmetry, then Z of A trivial as well. So in the absence of these domain walls, these gauge fields, the partition function is trivial, but it has a non-trivial response to the gauge fields. But if I break the symmetry explicitly, then I can't couple the theory to gauge fields for that symmetry, because I've broken it explicitly. And in that case, the statement is that the theory is completely trivial.
Okay, thank you.
Yeah, so we'll see how that works in some examples in a sec. Yeah, so okay, so here's a claim that I think is reasonable sounding, but maybe people have some different opinions that we can go into more detail about. But so we're considering a system with an energy gap, right? And we're considering a system where the partition function is just a complex phase, right? Now, the claim is that in this case, the partition function is going to be a topological invariant of the manifold that it's on. So I indicate this over here. So the partition function in the presence of these domain walls or this background field on some manifold like this S2 is going to be the same as the partition function on this kind of crumpled S2. And likewise, the partition function on this torus is going to be the same as this more ugly torus, right? Now, remember I said that there's no ground state, there's no non-trivial, the ground state degeneracy does not depend on the manifold that we're going to put it on. And so the magnitude of Z on a sphere, right, is going to be equal to the magnitude, or the magnitude is counting the ground state degeneracy, right? The magnitude of Z on a torus is going to be equal to 1, but the phase here can be different, and the way in which it's different is going to be a function only of the topology. Kind of intuitive way of understanding this is that you sort of have to, if you want to have like, you put your system on a torus like this, and then if you make some kind of local deformation to this torus, making some bump somewhere, then the system can only know about this bump here if it has degrees of freedom which are sort of can be localized and can know about the fact that you've made some local bump in the system, right? But we don't really have any local degrees of freedom here in these systems, because if we had local degrees of freedom, then we either wouldn't have a gap, or we would essentially we wouldn't have a gap, right? So when I don't have any gap and I don't have any really I don't have any local degrees of freedom, and so my partition function can't possibly be sensitive to local details of the manifold I put on. So what this means is that the partition function is going to be some, when I put these background fields in, this phase that I get for the partition function, this U1 number, is going to be a topological invariant of the manifold I put it on. Okay, assuming for now that the manifold is closed. So examples of such partition functions are, there's this one which we're going to look at in more detail in a bit. So this is some example of a possible candidate for an SPT partition function in 4 space-time dimensions. So here A is a U1 gauge field, and we're integrating over some 4 manifolds. And people probably know that this wedge product of the curvatures here is, so locally it's a total derivative. Locally it is A wedge dA, but globally it's non-trivial, and integrate this over a manifold, I'll get some number, and that number only depends on the topology of M4. Other examples, basically all the examples look something like this, where you have where the partition function in the presence of these fields is some integral of the fields that is a topological invariant. So another example that you might see if you're reading papers, you might see something that looks like this. So here A would be some, for example, some U1 gauge field. And then, there might also be some other, I'm not going to explain what this is, but this could be some like discrete data of the manifold. So maybe, in addition to U1 symmetry, there's some other discrete symmetry, time reversal or something like this. And then other kind of topological invariants can enter. blah, blah, blah. Anyway, the point is that what an SPT is, in the way I've described it so far, is it's a gapped system with no degenerate degrees of freedom, which when gauged, which when coupled to these domain walls produces phases like this for the So you can think of it
again. Sorry, I'm sorry. Question. Could you please explain again what are the domain walls? It is the domains where, like, could you give it like a stricter definition of it?
Like in terms of this A or something?
Yeah.
So domain walls are of course most easily illustrated for the presence of for a discrete symmetry, like I was doing earlier, right? But so earlier I drew this picture where I had, for example, let's just consider a Z2 symmetry. Okay, well then what I mean by A here for a Z2 symmetry is I mean some configuration of domain walls such that if you're up, then so if you're an upspin here and you move across this Z2 domain wall, you get flipped to a downspin or something. And so in the case where
upspin or downspin is not a property of A, right?
A is like this stuff, sort of. By A I mean a. So yeah, let's see, how should I? So what A does, right? What a gauge field does in general, right, is it tells you how to kind of, I don't know if I can use the word parallel transport, but it tells you how to like go from one place on a manifold. So here's some space, right? And I keep track of sort of the G charge as I don't know if I'm allowed to use like words like bundle and stuff, since Seth is emphasizing that this has to be very topological and stuff. But
if you want to, you can.
Why don't you just say like gauge fields link matter fields, so you have degenerate.
But in the partition, so what I'm confused by is that in the partition function, we already got rid of the matter fields, right?
Yeah, exactly.
So this is, so I'm struggling to understand how we could tell apart the domains when we already integrated out matter fields.
Yeah, exactly. So what one can do is so I said that Z was equal to 1. Maybe this is kind of a normalization choice, but what you should think of is like, we'll see an example of this in just a sec, where you have some matter fields, right? And then you have some action, and you have some Lagrangian with this matter fields and this gauge fields. And then you integrate out the matter fields, and they're all massive, and they produce some we'll see how this arises in a second, how matter fields, which even though they're massive, can still produce something like this. But I guess what McIntyre was saying is that, okay, the meaning of a gauge field is just, it tells you how to transport matter fields around, right? It tells you sort of how matter fields get acted on by the symmetry as they move around points in space, right? And so this is what domain walls are doing too, right? If you have some guy over here and you're moving along, then this gauge field tells you how this guy gets acted on the symmetry as it moves along points in space. For example, when it crosses this line, it will get flipped from up to down spin or something like this. And in the case, so this is easy to visualize in the case of some Z2 symmetry here. And in the case where I'm writing down things like this, which there's some continuous U1 thing, and in this case it's really the same thing. You just a gauge. If you can think of a gauge field as just inserting a bunch of twists in the phase as you move around space. So you can think of the same thing here in the U1 case, except this kind of becomes like action. If I have my matter field as phi goes to EDI, something like this, when I cross this thing.
I see. Thank you.
We're the next in order 2 slides, we're going to see an example of how this works.
Great, thank you.
So it's basically so what we have is topological response theory. So the way I like to think of things is an order one fraction of physics is computing path integrals with background fields, and SPT is just the simplest possible thing you can get when you do something like this. Okay, so the interesting, okay, 2 more slides until the example. So the interesting, one interesting thing about SPTs where they become a little bit more interesting is when you consider manifolds with boundary. So yeah, so let's consider placing this manifold on the boundary. Now, when I add a boundary, the assumptions that I had earlier about the system being gapped and non-degenerate and boring and everything, I'm going to make those assumptions in the bulk of the system, but I'm not going to make those assumptions on the boundary of the system. Okay, so here's the boundary. So suppose that yeah, nothing special happened on the boundary. So yeah, if this was the case, then okay, the boundary of a manifold so I have my SPT here on this boundary and on this manifold, and then I have a boundary. Okay, the boundary is essentially just like a domain wall between that system and a trivial gapped system, right? So if I have my SPT here, and then I have like this trivial vacuum phase, where the trivial vacuum phase is not only is it gapped and non-degenerate, but when I couple it to any fields, the response theory is also trivial. Now, if this boundary can be made non-interesting, can also be gapped and with nothing special happening there, then because I told you that the response theory for this SPT has to be topologically invariant, namely it can't depend on local stuff, then if I could make this boundary trivial, then what I could do is I could just, you know, the system can't care whether the boundary is here or whether the boundary is here, right? So I could, by moving the boundary, I could eat up the entire system and I would be left with nothing. So what this means is that at least if the symmetry is preserved so that the response action of the SPT is meaningful, I can't, the boundary has to be something non-trivial, sort of. Otherwise, I could eat up the whole system.
But this is not a rigorous proof, right? What you just said.
No.
It's
No.
just like a qualitative explanation.
Okay. Yeah. So if you want to know how this actually works, you need to learn about anomalies and anomaly inflow.
Can you say in 2 words what is consistent, the actual proof consists of?
Yeah. So
it can be complicated. I won't be asking too many questions, but just statements.
No, I was saying at the beginning that we want to have like a discussion here. So so let's see. So yeah. Well, maybe it'll become this will become a bit more reasonable in the following. But what we'll see is that this. Well, it's a kind of a general fact about these topological response theories that I wrote down above, that you can sort of imagine when I give the system a boundary, then my response action is looking like e to the I integral of some manifold with boundary times some topological Lagrangian for these fields. Now, if M is a boundary, because this is topological, it can be the thing appearing in these brackets can locally be written as a total derivative of something. And so in the presence of this boundary, I can write this as like e to the I integral of dm of the thing appearing in here, right? I can kind of integrate out things onto the boundary. But it's a general property of these response theories that this thing here is not well defined by itself. That that sort of just comes from writing this thing writing this topological response action as a total derivative. When you write this as a total derivative, the thing inside the derivative is not well defined, because I can add sort of derivatives, exact forms, if you will, to this stuff and change the thing that's in here while preserving this. And so that means that the thing that I get when I look at the boundary is not well defined. And this means that the boundary theory by itself is not well defined. So it doesn't really make sense to consider the boundary theory by itself. And that's sort of another way of saying that the boundary theory, the thing on the boundary kind of has to be special in some way. But intuitively, I think this argument about if the boundary was if there was nothing special on the boundary, then because of the topologicalness of the SPTs, the boundary could be kind of deformed and eat up the whole system. I think this is sort of sufficient for what we're doing right now, and we'll see an example in a sec.
Good, thank you.
These are the keywords. So sort of what I was just trying to say is this statement here. The statement is that when I have a manifold with a boundary, then I add these domain wall things, this background field, then the partition function does not factor as this product, right? So if everything sort of was local and things, degrees of freedom in the system sort of didn't, well, let me not say anything about, but if one thing that you might expect, given that this system that I'm considering doesn't have any low energy degrees of freedom and stuff, is that the partition function on some kind of collection of some sum of manifolds like this would just be kind of a product of the partition functions. And in the case of the boundary where I had some boundary, the partition function would be something on the bulk times some separate thing that's living on the boundary. But that cannot be the case for the reason that I was saying above, is that if this was the case, then what I could do is I could make some local change to the I could make some local change to the boundary. I could come in with add some degrees of freedom here with partition function equal to the conjugate of this thing, and cancel this boundary off. And in that case, I could again do this thing where I sort of grow the boundary into the system and make the whole thing trivial. So that's not possible. Again, this is sort of this is trying to say what an anomaly is without actually being careful. But if people want to actually understand more, these things are called 't Hooft anomalies. And the best way to learn about these is to look at the paper by Harlow and Oguri on this. They're on symmetries in quantum gravity. This paper is very good for learning about these things. You don't have to be interested in quantum gravity to read this paper. Okay, so finally we're going to do an example, which is my favorite example, and is the OG example. And that example is the topological insulator. So this is why like SPTs are a big deal, in my opinion. So okay, so the TI is a symmetry protected topological phase. So the S in the symmetry protected topological phase is this group here. So we're going to be considering a system where we have some U1 charge conservation symmetry, and we're also going to have time reversal symmetry. And I think I wrote the direct product, the semi-direct in the correct direction, but what this means is that the time reversal symmetry doesn't commute with the U1 symmetry. Anyway, we have these two symmetries, and what we're going to consider is a microscopic action that is just a Dirac fermion with a mass. Okay, so the Dirac fermion can be coupled to, okay, so first, suppose I got rid of this A here. You ignore this A, pretend I didn't write that. Then what this theory would be it would be a massive Dirac fermion. Okay, and so that fits the definition of being trivial in the sense described above. There's no degeneracy on any kind of manifold. The theory is gapped, no local degrees of freedom. Okay, but as I was saying above, the thing that's not trivial about SPTs is that you can couple them to background fields and study the response. So here the symmetry is U1 times this time reversal thing. I don't want to explain how to add gauge fields for this time reversal part, but it will suffice for our purposes to just consider what happens when I add a background field for the U1 part. So that's what I do, and of course we know that this is how you do it. You do this minimal coupling thing in the action. Now the claim is that even when I make this mass to be very, very large, so that the fermions are totally gone, there's this kind of magical statement that the partition function is still non-trivial, even when the mass goes to infinity. Now, more precisely, since we're working with Dirac fermions, this mass does not have to be positive. Indeed, it can be negative. So because the fermions, the spectrum of fermions are kind of like half a boson, and so the spectrum always has m squared in it, right? And so I can take m to be positive, or I can negative, or it can even be m is actually just I can take it to be some complex number. And when I do this, I can study the partition function as a function of m. Oh, sorry. M can be any complex number, but I'm going to assume time reversal symmetry here. So m is going to be any real number. Right. Okay. And then the claim here is the following. So the claim is that if I consider this ratio of partition functions here, the ratio of the m goes to infinity to the m goes to minus infinity, then this is actually a non-trivial thing, which is this, and this it would be written above as this z of a, and this is going to be, well, maybe I'll write it as ZSPT of a, and this is going to be some U1 phase. And this is exactly the topological invariant that I wrote down a little while ago. This A wedge dA, we're in 4 dimensions, 4-dimensional spacetime, this A wedge dA thing. And this is kind of the topological response of the topological insulator. So, okay, so why, if the fermions are infinitely massive, both in the numerator and in the denominator, then how can we possibly get anything interesting out? And so the reason why this works is the following. I'm going to assume that people have learned about the chiral anomaly. If that is not true, we can discuss how this works briefly. But the idea to prove this statement here is to perform a chiral rotation. Okay, so a chiral rotation is the U1 symmetry which acts on the left component of the fermion and the right component on the fermion with opposite phases in this way. Now you notice that when I do this, what happens to the mass term? So here's the mass term, right? Remember that a mass for fermions for example, in 4 dimensions couples the left component of the fermion to the right component of the fermion, right? Because gamma bar gamma is like gamma dagger, maybe sigma x, something like this, gamma. So it couples the left and the right components, so it looks like this. Now, if I perform a chiral rotation by, I guess, where if I choose alpha to be pi over 2, then this guy becomes minus of itself, this mass term. So what this means is that the mass goes to minus the mass under this chiral rotation. So the chiral rotation allows me to relate this partition function to this partition function. And so the claim is that doing the chiral rotation, though, produces this thing on the right, right? So okay. So why does that happen? Well, it's because of the chiral anomaly. So the chiral anomaly, what the chiral anomaly tells you is that it tells you that the current for this U1 chiral symmetry is not conserved. And the reason that it's not conserved is because when you do a transformation like this, one way to think of it is which is not completely satisfactory, but one way to think of it is that the measure for these fermions picks up this phase. And okay, so you can read about this in certainly any quantum field theory book. I don't know if it's discussed in condensed matter physics books yet, but
David
what happens
Tong's
is
notes have also very good discussion.
Yeah.
His gauge theory notes.
That is not surprising. So anyway, so hopefully people know about this, but if you don't, go read David Tong. And because of this phase, this means the ratio of these two partition functions is this thing. This is the same phase. I've just taken this theta equals pi here to be given by the pi over 2 of this alpha that I need to relate the two things. So the conclusion here is that this is what happens by the chiral anomaly. Okay, so now okay, great. Well, okay, I'm not going to talk about that yet. So now what we can do is we can consider a domain wall where this mass changes sign. So here I'm drawing this picture in space, right? But we're in 3 + 1 dimensions, so there's also a time dimension, right? But we consider a scenario where m is going to go to, for example, infinity over here, and then over here m is going to go to -infinity. And we can choose our conventions such that when I take m goes to -infinity, the partition function is 1, and when I take m goes to +infinity, the partition function is this number. The reason that I can do this is that this number here actually turns out to be ±1. If you look at how this f wedge f guy is quantized, this phase is always ±1. And so what this means is that basically because it's ±1, there's a z2, and I can choose either side to be the vacuum. Anyway, I'm gonna have vacuum over here, and I'm gonna have this SPT thing with this response action over here. And let's see. And yeah, let's see. This is kind of the picture that I was illustrating earlier. And what this is kind of like saying is that there are, let me just explain these comments that I wrote down here. This comment is saying that the situation that we find ourselves in is sort of like saying that there are multiple super selection sectors. So a super selection sector is like, a certain one of a collection of spontaneously of ground states for a spontaneous symmetry breaking state. And this is kind of like what's happening here. We have two sort of different ground states. We have this m goes to -infinity thing, and we have this m goes to +infinity thing, and they are different, but the way they differ is by this phase thing. And as I was saying above, this phase, there are no local degrees of freedom or anything in either side, and so this m goes to +infinity and this m goes to -infinity side are locally indistinguishable. The only difference is this kind of global thing. Yeah, I guess I don't really have anything else to say on that. I'm going to talk about this boundary more closely. I was saying above that boundaries of SPTs had to be non-trivial in some sense, and so let's see how that works in this context. So what is the boundary in this example? Well, the boundary, I'm considering a domain wall where the mass is infinity, and then it goes to -infinity, right? So the boundary, the mass is 0. And in particular, what this means is the boundary is the action of the boundary. If we just focus on the boundary, is given by this. So psi boundary is the field restricted to the boundary. And then this term, which you'll recognize as a Chern-Simons term divided by 2, a Chern-Simons level 1 term divided by 2, is what I get when I take this guy and integrate it and sort of integrate this onto the boundary by Stokes' theorem. So this is a total derivative locally, as I was saying earlier. But so this means I can integrate it and write it as something on the boundary. And the thing that it is when I write it as an integral on the boundary is this Chern-Simons guy with level 1/2 Chern-Simons. Okay, and so now let us ask whether this theory here, this S partial, is sort of trivial or can be made trivial in the sense that I was talking about above, where I wanted to know whether or not the boundary could be sort of, eaten into the bulk, whether there was anything interesting happening on the boundary. So let's do some checks on this action to see this SB and S partial and see if it's interesting. So one way we can make this S boundary non-interesting is to add a fermion mass to the boundary, right? To just extend the mass into the boundary, or just to add a 2 + 1 dimensional mass for the fermions on the boundary, right? Okay, but then this is actually impossible within the confines of our problem, because in 2 + 1 dimensions, a time reversal actually acts oddly on the mass term for fermions. So I can't just add a mass term to gap this system out without breaking the symmetry. One thing that I can do is I can add, instead of adding a number here for the mass term, I can add some dynamical field like this, where phi is odd under time reversal. Then this thing will be even under time reversal. It won't break any symmetries, and I can add it to the action. And in particular, I can consider a scenario in which maybe I have spontaneous symmetry breaking for this field, phi. So this might happen, for example, if I take my boundary and I do some local perturbation to the boundary by adding an antiferromagnet or something to the boundary. So I'm not touching the bulk. I'm just adding some degrees of freedom on the boundary that happen to come in the form of an antiferromagnet, where this phi is some kind of coarse-grained field for the antiferromagnet. And then if I consider some phase where this antiferromagnet is in the spontaneously symmetry broken phase, then this phi here sort of behaves as a constant, and the side fields are massive by virtue of coupling to this field. And then what I'm left over with is this thing that I wrote down above, this half Chern-Simons thing. And this half Chern-Simons thing would tell you that the Hall response on your boundary is 1/2. And this actually cannot happen in any 2 + 1 dimensional theory. It's impossible to have a fractional Hall response, essentially because this, well, I guess there are multiple ways of thinking about it, but this action is actually not well defined in 2 + 1 dimensions because of this 1/2. Really, this thing that I'm writing down here can only really be interpreted as the result of doing Stokes' theorem on something like this. So this thing doesn't make sense by itself in 2 dimensions. And okay, so this is not really, I'm not really giving any precise argument. The precise arguments for why this S boundary is non-trivial involve what I was saying above about 't Hooft anomalies. But you can kind of play around and convince yourself that this S boundary is non-trivial, and that the fact that it is non-trivial cannot be changed by doing anything local to the boundary or without breaking the symmetry. Okay, so the topological insulator is okay. So one consequence of this, of course, why everyone likes topological insulators is because the boundary is this theory with this massless fermion, and as we discussed, you can't make this fermion gapped out and trivial. And so this is why topological insulators have conduct on the boundary, right? Because if I have a topological insulator, then and this is the boundary, then the boundary has to be non-trivial. If there's no time reversal symmetry breaking, it's gapless. And so then, even if I put local stuff on the boundary, like a bunch of impurities, the gaplessness of the boundary is not going to change. And so I have conduction even in the presence of impurities, which is interesting because Anderson said that it shouldn't happen and blah, blah, blah. Any questions about the topological insulator example? I'm gonna, well, if not,
Oh,
stop.
sorry, I have a naive question.
Yeah.
Yeah, maybe I missed it. So you said if you couple this fermion to a scalar field, and then you consider the spontaneous breaking of this time reversal. But then you then phi has some like average value, right? And then you want to integrate all the psi fermion. But this, yeah, I mean, if this psi is Dirac fermion with a mass term, right? So why do
so that'll produce
so
some
why
like
don't
integer.
but you only have one. So how many flavors do you have?
I guess I just want one flavor. So my understanding is that then when you do this, I mean, it depends on when you do this, the correct way to do the regularization is that what this then produces is a theory where you have sigma xy is equal to a half plus some k, where k is in C. I don't know if this is what you're getting at.
But if you only have a single flavor of Dirac fermion, if you integrate out, you should get sigma xy equals a half, right?
Well, I think this depends
Something
on
like
exactly how the regularization works, right? So
yeah.
So the claim is that the correct way to do the regularization is to so the claim is that you are allowed to spontaneously break time reversal symmetry, but you're not allowed to explicitly break time reversal symmetry. So you can and then the statement there is that when you do the regularization with like polyvolaris or whatever, then if you don't explicitly break time reversal symmetry, the total Hall conductance should be a half integer. Well, should be a half integer coming from this plus an integer coming from the weight.
Yeah, so by polyvolar, you're considering adding another massive Dirac Hall. Right? This is the regularization from polyvolar. So they have opposite mass. That's why you get something that's why it cancels out for this Dirac Hall you have. Because you're saying yeah, sorry, I don't know if I understand you correctly.
So I think I'm saying that if you have I think I'm saying that if you have this massive Dirac fermion made massive by this dude, and you integrate it out, you shouldn't change the fractional nature of the response coming from the topological insulator, right? Because well, I mean, because the spontaneous, I don't know, maybe I need to think about this more. Certainly the fact that you have this anomaly and stuff that is telling you about the sort of fractional quantum number coming here is a statement that doesn't depend on whether you have spontaneous symmetry breaking or no spontaneous symmetry breaking, right? Because it's a statement about commutation relations of operators and stuff. But you're saying that if I have this, but you're saying that if I explicitly added a mass, let's ignore this phi guy. You're saying that if I just consider this guy, I would be able to, since I've already broken time reversal symmetry, I could.
Yeah.
No, but then I
Yeah.
still, if I do that, I still generate an integer Chern-Simons term, right?
Why?
Like so if I choose to regulate in a way that does not break time reversal symmetry, then I get a half integer. If I get a half integer Chern-Simons term. But if I regulate in a way that breaks time reversal symmetry, then I get an integer Chern-Simons term. So the claim is that in both of these examples, the way that I'm regulating is in a way that breaks time reversal symmetry. So I should get an integer Chern-Simons term.
So so the integer Chern-Simons is without the half, without the first term.
Yeah. So I'm saying that there, we have this usual story of the parity anomaly, right? So we can either break U1, by having this 1/2 LCS, or we can break T, right? And I guess my claim is that in this case we've broken T explicitly, and here the regularization that we're doing is a T breaking regularization, and so when we do this, we don't generate any half term for the Chern-Simons, and the fractional part of the response is just coming from the bulk part. Does that make sense?
Okay, but more like but a simpler question is that you have a TR in the bulk, and if you just break the time reversal symmetry on the boundary, can you get a trivial action on the boundary? So you're saying this SPT is protected by U1 and semi-direct product time reversal. So if the boundary breaks time reversal, it seems that it can be trivial, right?
Well, I guess I don't know. I guess I don't know a way of getting rid of the half part of the Hall conductivity.
Yeah, what I'm saying before is that if you just have a Dirac fermion, a 2+1 in 2+1D, and you don't do any regularization, then you'll get half sigma xy if you just integrate out.
Maybe the claim is then that is not a legitimate system to consider. That regularization would not be the correct regularization to do in 2+1 dimensions, right? Because definitely we need to be able to integrate out the claim is that the correct thing to do is to choose a regularization that preserves gauge invariance, sort of. It's not the best words to use, right? But the claim is that if you're just considering a pure 2+1 dimensional system, you should never choose a regularization in which you get a half integer Chern-Simons term.
Yeah, but now you have another half integer also in the action. So
yeah. So then I would say that that's the whole point. I guess that's the whole point of the anomaly. Yeah.
Yeah, I see. I need to think about more carefully. Yeah, thank you, folks. So I have to go.
Yeah, later.
Yeah.
Thanks
I'll
for the
catch you later then.
Yeah, cool. That'd be good. Yeah. So maybe to add on what Dan was saying is that I guess I should emphasize that the way in which, well, maybe, I should say that this S in the SPT is really a symmetry of the whole system, not just of the bulk. And so in particular, you can do things like you can break the time reversal symmetry on the boundary by adding on some integer quantum Hall state or something just to the boundary, and this is going to change this sigma xy by an integer, and that's sort of not, that's kind of not relating to the anomaly. Okay, anyway, that's, don't have to talk about that now. And since it's one, I'm just gonna, I have 2 slides and I'll just finish. So if people want to learn more about SPTs, then you will see that essentially all the examples of SPTs are sort of just variants on this topological insulator kind of idea, where we have some degrees of freedom, we couple them to a gauge field, we integrate out the degrees of freedom, and then we get a topological response to the gauge field. It's not always discussed like this, particularly in these examples, which are popular. So people may have heard of the Kitaev chain, which is a chain of Majorana fermions with this Hamiltonian. The symmetry, the S in the SPT is this fermion parity. There are some spin chain models. There's this famous Haldane chain, where the Hamiltonian is this. These are spin 1 operators. There's the S in SPT is this. Yeah, if you want to sort of explore SPTs more generally, then there are sort of 2 plans of attack you can take. One plan of attack is to try to write down sort of general lattice models that give you these kind of topological responses. This is the style of Xiaogang and his affiliates. And another perspective is to try to approach them more formally in kind of like a more algebraic language. This is the style of like Dan Fried and people. And my understanding is that the formal sort of classification of these things, at least in, maybe there are some subtleties when you have some fermionic degrees of freedom and stuff, but essentially the general classification of SPTs has kind of been solved sort of within this framework. And then, okay, last slide, just to clear up some confusion that I remember I had a while ago, is that so there are things that look like SPTs in a lot of the senses in the ways that I've described them above, but are in fact should not be called SPTs in the definition of today's discussion. One example is the integer quantum Hall state. So we can ask, is the integer quantum Hall state an SPT in the definition that I have been giving? So the integer quantum Hall state does not have any, fractional excitations or anything, that you have a unique ground state on any manifold. And this ground state is gapped. And the ground state, you cannot tell the ground state apart from the vacuum using any local measurements or anything. So it seems to fit the bill of an SPT, but in fact, it is not really, it's not an SPT because there is no S, there's no symmetry that is protecting this setup. So the integer quantum Hall state, right, has chiral edge modes like this. And these chiral edge modes cannot be gapped, made trivial. So the edge part of this system cannot be made trivial with any local perturbation. This is, okay, well known. And so there's no local perturbation that can gap out these edge modes because they're chiral, and sort of because chiral fermions, can't be, to make fermions massive, you need a left fermion and a right fermion, right? To make them massive. Anyway, so the integer quantum Hall effect is not really an SPT because there's no S. There's a bosonic example of an integer quantum Hall effect that is sort of an SPT, but I guess I won't get into that. Okay, and then I'm done. So thank you for sticking with this hot mess of a talk. And do we have any last questions here?
I have a question about the phi couples to psi case. So what actually prevents us from adding like such phi, adding such antiferromagnetic operations to psi?
What prevents us from doing that?
You said that this is not allowed because we well define something like that, but physically we can assume we just add some operator there. So what's the control?
Yeah, sorry. I mean, this probably became very confusing at the point where I was talking with Dan about all of this stuff. The claim is that this actually is an allowable thing that you can do. But so in particular, you can do this without breaking any of the symmetries, right? Because this phi is T odd. And depending on the dynamics of the exact details of phi that I add, then there may or may not be spontaneous symmetry breaking for phi. But the point is, this is what, and maybe need to offline think about what Dan and I were talking about. But the claim was that the boundary theory can actually not be made trivial if you do this coupling. So we wanted to know whether or not it was possible to kind of make the boundary theory trivial without explicitly breaking the symmetry. And the claim is that if you don't explicitly break the symmetry, the boundary theory is still non-trivial because its Hall response is something like this. And this 1/2 part of the Hall response coming from this term is impossible to get rid of while staying in the while only considering stuff that is localized to the edge. So you can prove that in any strictly two-dimensional system, this sigma xy thing has to be an integer. And the fact that it's not an integer tells you that there's some non-trivial stuff coming from the bulk that kind of can't be done away with. So this is totally allowed. Yeah. And I should make, sorry, go ahead.
So an SPT phase do have like an half integer boundary.
Yeah. In this case, yeah. Okay. So the thing is that in any SPT phase, when you look at the boundary, this boundary has to be non-trivial, whereby non-trivial, I mean that it's sort of like can't be canceled by a 2D thing. Sorry, canceled by, in this case, a 2 + 1D thing. So there's nothing that I can like stack onto this boundary to make the boundary trivial. And in this setting, it shows up as this 1/2. Yeah, and there is kind of an important but subtle distinction here between explicitly breaking the symmetry and spontaneously breaking the symmetry. But I don't know.
Okay, thank you.
Yeah. Oh yeah, I should have talked about this picture here. This picture is, so here's our TI and here's the trivial state. And the claim is that as long as I consider perturbations which don't explicitly break T, there is no way to smooth, there's something here that is preventing me from smoothly going from the TI to the vacuum. But it's totally possible to, if I kind of, as I was saying, if you consider T breaking perturbations, it's possible to smoothly go between these two. For example, without closing the gap, right? So for example, I can just take, I told you earlier that this mass term, now we're in four dimensions again. This mass term here, this could be any complex number. And so in particular, if I consider taking the mass to be very, very negative, and I tune the mass this is the complex plane. If I tune the mass like this while keeping it away from 0, then I can smoothly connect the TI to the vacuum. Of course, when I do this, if the mass is complex, this term breaks time reversal symmetry. And so I have to explicitly break time reversal symmetry to do this. But if I'm, but as long as I consider a time reversal symmetric case, I'm confined to the real axis here. And then if I try to connect these two, I have to run into this place where the mass goes to 0. And so it's impossible to smoothly do this deformation. Okay, any other comments, questions?
So you drew this, okay, this is probably a naive question. So you drew this point that prevents you from going smoothly from topological insulator to vacuum, right? So this is a topological phase transition, right? Or what is this point? Like, is there some...
Well, this point is just a massless direct fermion. So the thing that's living here. So when I said smooth, I just mean don't close the gap. And so this point here is just psi this guy.
Yeah, but basically this point allows you to like separate different behaviors of the system, right? So it's like
yeah, that's right. Okay. Yeah, I guess you should use the word topological there. Yeah. That seems I that adjective makes sense to me.
So is the S in this example the U1 times Z2 or the Z2 or the U1?
Yeah, it's both of them, right? So together. So yeah, what's the best way to explain this? So, well, we said here that we need the T. So it's SPT, right? So the P is protecting. So the symmetry has protecting. So as I was just explaining, the T is needed because otherwise I could do this thing, right? Where I add this mass term and smoothly connect the two. So the T is needed, and the U1 is needed at the same level. So if I, for example, if I allowed myself to break U1, well, if I allowed myself to break U1, then I could, again, getting into discussions that Dan and I were having, if I allow myself to break U1, this 1/2 thing actually, which we were saying is kind of like very important because this 1/2 sort of cannot be, is not, if I have this 1/2 on the boundary, it's something, it means there has to be a bulk, and it's kind of responsible for the non-trivial physics of the boundary. This, if I allow myself to consider breaking the U1 symmetry, then actually I can regulate the path integral in a way that this 1/2 disappears. So you can think of it, this 1/2 means that this this term is sort of not gauge invariant. And so if I allow myself to add terms to the action which break U1 explicitly, then my action will not be gauge invariant, obviously, because I've explicitly broken the symmetry. And you can add these terms in a way such that this thing dies. And so if I break U1, then the topological response action can just be made trivial. So I need both symmetries. And yeah, what happens in SPTs very often is that you have two symmetry groups. Well, you have a symmetry group that factors as a product like this, and sort of the SPT is protected by the interaction between these two symmetries. Again, this is how one thinks of 't Hooft anomalies and stuff. In this case, it's both U1 and Z2T.
Okay, that's clear. Thank you.
Yeah.
All right, cool. If there are no more questions, then I think we'll call it for today. Thank you, Ethan. That was really good.
Yay! I can prepare a talk in 30 minutes at 12:30 and people still have fun.
All right. I will see you all next week. I think Jameson is giving a talk on photonics. So that should be off the beaten path for the way that we've been going so far. All right.